Assalamu alaikum. Today we will be presenting our project, a 4-bit logic-based binary to decimal converter. This project was done by Rehan Ahmed Malik, Abdul Rafi and Raja Jazib Ali Nasir. Our project involved designing a converter that can take 4-bit input value and display its corresponding decimal values on a 7-segment display. We used logic gates to implement this. Additionally, we expanded this design to a frequency meter, which measures signal frequencies and displays it digitally. This project addresses the challenge of converting binary data, which is common in digital systems, into a decimal format that is easily readable by humans. It is particularly useful for understanding how real-time displays work in embedded systems. By adding a frequency meter, we applied our design to a real-world scenario, measuring and displaying frequency values using digital logic. In real-world applications, frequency counters plays a critical role in monitoring signal properties in embedded and digital systems. Such systems are commonly found in digital clocks, measurement devices, and any scenario where binary data must be converted into human-readable decimal form. The frequency meter, in particularly, is widely used in diagnostics and signal processing tasks. The components that were used in this project: for binary converter we used 4 NOT gates, 16 AND gates, and 7 OR gates to derive 7-segment display. For frequency meter part we used 555 timer for pulse generation, capacitor and resistors for timing control, transistors for switching, and additionally 7-segment displays for output. Thank you.
Assalamu alaikum. This is Jazib Ali, 23i-6011, showcasing the Proteus sim of the BCD to 7-sig display specific portion of our group's DLD project. As you can see, we have inputted 4 input lines for the 4-bit display from 0 to 9, and we have the multiple AND gates, OR gates, which are all leading into the 7-segment display. I'm going to zoom in now and show you the outputs. In this case, D is taken as D1, C is taken as D2, B is taken as D4, and A is taken as D8, as it is providing those specific inputs. Okay, I'm going to run the sim now. And now that it's running, give it a moment. It is providing the 0 output, as you can see here, as 0 is being provided. Now if I provide a binary input of 1, it goes to 1. Now if I remove that and go to 2, it goes to 2. Now if I go to 3, it goes to 3. If I remove these and give an input of 4, it goes to 4. And if I give 5, it goes to 5. 6, it goes to 6. And finally, D9, which is the limit of a 7-sig display. In this specific way, we have the 9 input for 1001. We are currently at 0 input, so it reads as 0. I'm going to change it to 1, and now 4, and now 5, 6, 7, 8, and finally 9. That concludes my BCD to 7-segment display.
Assalamualaikum everyone, I am Rehan Ahmed Malik, roll number 23i6179, and I will be explaining the Proteus simulation and the hardware implementation of our project frequency meter. Starting with the simulation, this is our basic circuit. We used counters with 7-segment displays, a 555 timer IC, and an input signal. For this demonstration, the input has been set to 1000 Hz. The basic working principle behind this is that the counters increment when a rising edge is observed in the input signal. And using a clock, we reset these counters after 1 second, giving us the frequency or the number of waves passed in 1 second. Okay, so now we will run the simulation using a signal generator as our clock set to 1 Hz. As you can observe, the counter counts towards 1000 and then resets. Now we will use a 555 timer IC as our clock, and as you can observe, the counter only counts towards 990 and then stops. This happens because the timer IC is not very accurate. Okay, so now moving on to the hardware. This is our circuit before connecting the 7-segment displays. As you can see, we have 555 timer ICs on the left along with potentiometers to fine-tune the frequency to exactly 1 Hz, and we have counters on the right. Now moving on to the demonstration, we used clock generator of a trainer board as our input signal. And initially it was somewhat stable at 790 Hz, and when I increased the range of the generator, it started increasing. There's a lot of room for improvement in this project. First of all, we should have used crystal oscillators, but we couldn't find them, so we had to opt for 555 timer ICs. Moreover, we should have used signal generator for input instead of a trainer board, and we could have added more counters and displays for greater range, more than 1000 Hz. This concludes our project. Thank you and Allah Hafiz.